So far, we've talked about non-seasonal ARIMA models and non-seasonal data, but ARIMA models are also capable of modeling a wide range of seasonal data. So in addition to having your regular ARIMA models, you also have a seasonal component of an ARIMA model. So the model is called S-ARIMA, which stands for seasonal ARIMA. And what it does is it includes a seasonal term. So what we are familiar with is ARIMA PDQ, where P refers to the autoregressive component, D refers to the order of differencing or the order of integration in the data, how many times we need to difference our data to make it stationary, and Q refers to the MA component. Okay, so this is the non-seasonal part of the model. But you can augment this model with this right here, which is all in capitals. When it's in capitals, this is referring to the seasonal part of the model, where M represents the number of observations per year, or the seasonal component. So M is going to be 12 for seasonal, for monthly data. M is going to be 4 for quarterly data. Okay, and this is going to be corresponding to the seasonal components. So again, the AR component, the differencing, and the MA component for the seasonal part in the ARIMA model. So there are various ways of writing the ARIMA models. The backshift notation is very popular for writing more complicated seasonal ARIMA models, because you can write this in one sentence or in one line. Here, if you wanted to represent an ARIMA 111, 111, 4, you would do this as follows. So what you have here is representing the AR component, the seasonal AR component, the first differencing here, and the seasonal differencing here. Okay, and then on the right side you have the corresponding MA component, which is the regular component, and the seasonal component. Okay, so this is the representation here, and this is much cleaner than writing it out like this, where it's all muddy. Okay, so some common ARIMA models that are used by the US Census Bureau are written out here. These are all models that are used with log transformations once you've stabilized the variance. And these are very popular models. If you look at these are so simple. These models are so simple because these don't contain as many lags for seasonal or for regular components. Okay, very popular models, and this reminds us that in forecasting, the best models sometimes are the ones that follow the principle of parsimony. Now, just thinking about the seasonal ARIMA models, the seasonal part of an AR or MA model will be seen in the seasonal lags of the PACF and the ACF. So PACF, again, and ACFs are very important in determining the lag structure for either seasonal models or for the regular AR MA models. Okay, if you had a model which was monthly data, which was showing some seasonality, you would see a spike at lag 12 in the autocorrelation function, but no other significant spikes. The partial autocorrelation functions would show an exponential decay in the seasonal lags, which is at lags 12, 24, 36, and so on. If you had an ARIMA model which had an AR component, okay, not instead of an MA component, you would see an exponential decay in the seasonal lags of the ACF, but a single significant spike at lag 12 in the PACF. Okay, but with more practice, you're able to see these. Now, if we look at a data set called European Quarterly Retail Trade, you can actually plot this data and see whether there is any seasonality present and what type of patterns this data would follow. You can actually use the gg_ts display command to plot your data and take a look at the autocorrelation functions. In this case, you're seeing an exponential decay in the ACF. So if you're seeing an exponential decay in the ACF, this is pointing you to some, well, this is not saying anything yet, but the idea here is to also look at the PACF, okay, and find the appropriate MA model, ARIMA model. So if you look at the PACF here, you would, which is not here, but if you plot it by just putting this argument plot underscore type equals partial, you would be able to see the partial autocorrelation function. Go back to the slide that talks about what models there are and how to determine the lag structure for the seasonal ARIMA models. You would be able to do this on your own. You can also difference the data. Obviously, this data did not look stationary, so we do know that this needs to be differenced. You can take a look at the differenced time series, first the seasonal difference and then the regular difference. This would be determined by, again, KPSS tests and using the KPSS underscore, the NSDIFs and the NDIFs commands. You can determine how many times you have to difference the time series, and then you can actually run your models this way. Okay, we're still not running the model, but we're just differencing it at this stage. Okay, so the data look much more horizontal in this stage after the differencing has been done than at this stage, okay, or at this stage. So this is just with seasonal differencing. This is with seasonal differencing and the regular differencing. Okay, so it does seem like both types of differencing, seasonal as well as regular differencing, seems necessary. A significant spike that you see at lag 1 in the autocorrelation function suggests that you may have a non-seasonal MA1 component. A significant spike at lag 4 in the autocorrelation function suggests that there might be a seasonal MA1 component. So here is what you're seeing. Okay, so you see it at lag 1, at lag 4, and this is quarterly data. Okay, so you could have a model which is something like this: ARIMA 011, 011, and quarterly, or you can have an alternate model. Okay, you can then represent the model that you are guessing in this fashion. So you can have the regular PDQ components and the seasonal PDQ components represented here. And then you can take a look at the residuals. So you see, instead of one spike, apart from one spike, everything else lies within the Bartlett band. So we're okay, I guess. And then you can do a Loombox. Loombox is like really marginal here, okay? This means that the model barely passes the Loombox test. Okay, but we can still use this for forecasting purposes. Now, whenever you have this type of a situation where the autocorrelation functions are showing some spikes for the residuals, which is in this case, we're taking a look at the residuals, remember, not the time series itself. When we're getting 1 or 2 spikes, we can always change the model and add more lags to see whether the model performs better. So in this case, what we're doing is we are adding more lags to the MA component and seeing what happens to the AICC. So this is clearly the winner, this model, 013011, with an AICC of 68.39. You can model this, and you can take a look at what happens to the residuals when you have such a model. So you can say model ARIMA. This is a nice way to name the model so you know what you're doing. ARIMA value PDQ 013, and then PDQ for the seasonal component is 011, and then you see that the AICC is 68.39. So you can estimate the variety of models and see which one gives you the lowest AICC. Now when we look at the residuals, it looks a lot better, where your residuals do fall, or the autocorrelations do fall within the Bartlett bands, and the Loombox value is 0.9. So just almost 0. This is a high p-value, so we don't have a problem with in this model, we had a problem with the p-value, but being 0.1. But in this model, we have a high p-value, so the model clearly passes the Loombox test. So there is no autocorrelation in the errors. And so we can use this to forecast. In this case, we're forecasting 3 periods ahead, and it shows you the 80 and 95% prediction intervals. So notice, as long as you have something that's 1 in here, you have a seasonal ARIMA model. Now you can also take a look at or try to search within a broader class of models by using the stepwise equals false function and approximation equals false function, and this gives you 0, 1, 3, 0, 1, 1. So it doesn't really change what we had before. There's another application that I have in the slides, which is a data set that you're used to. This is corticosteroid drug sales in Australia between 1991 and 2008, where we're looking at the cost of these drugs over time. So in the first panel, you have the cost. In the second panel, you're trying to stabilize the variance by taking the log of the cost. Now we take a look at the difference in the log, right? So we know when we look at this type of data, we know that this is not stationary, so we need to difference it. You can use KPSS tests, and you can use the NDIFFs command to NDIFFs and NSDIFFs commands to see how many times you want to difference the data. But here we're just differencing it once and see that it starts to look a little more horizontal. We can probably do better. You can also take a look at the PSEF to see what types of patterns exist. So there is definitely zero correlation in the data, which we can exploit in our ARIMA models. Okay. So we have spikes. If you look at the PSEF at home, you would see that there are spikes at lags 12 and 24, which is suggestive that we should have a seasonal component in our model. And the spikes in the PSEF would suggest that there's a non-seasonal AR3 term. So you can take a look at what types of candidates there are. There's a host of models, right? If you were doing this manually, you can estimate these models and see which model gives you the lowest value of the AICC. In this case, for negative 485.5 is the lowest value that we get, and so ARIMA 301012 is the best model. Now we can fit this model to the data and try to take a look at the residuals. Now you see that the residuals, the autocorrelations are falling outside the Bartlett bands in some cases, and the Loombox is 0.01, okay? And so this is telling you that the residuals are autocorrelated and prediction intervals would be inaccurate for this type of data. So what can we do then? We can then try to automate this and take a look at what does the ARIMA automatic function give us when we just put in log cost, okay? And we're not doing guesswork. If we keep doing guesswork and we're not able to come to a model that gives us white noise residuals, then we need to rely on this automatic method, which would go through this entire class of models and see which one is the best model, okay? So here we're just doing ARIMA on log cost, and this tells us that 210011 might be the model you want to look into. Okay, now we can do residual diagnostics. There are still spikes that are outside of the Bartlett bands. And again, this is showing you that even with the automatic model, the model fails the Loombox test. Okay, now what we can do, the next step is we can use these arguments and search over a large class of models. Stepwise equals false, approximation equals false, and we can always make there can be a restriction that can be given on the parsimony of the model. So to make the model parsimonious, we can say p plus q is less than equal to 9 and search for a model that satisfies this along the different class of models that the algorithm will look over. And so in this case, the AICC is negative 487. In the previous one, we had 482, so this model is doing better. We can take a look at the residual diagnostics. This seemed to look better because there's only one spike out here. Okay, and then you have your p-value, which is 0.13. So it's greater than 10%, which is good, which is telling us that the errors are pretty much white noise for a lag of 36 errors. Okay, and the degrees of freedom that we have used up are 9 because we've restricted it to less than or equal to 9 parameters that were estimated. And look, we have estimated 1, 2, 3, 4, and 1, 2, 3, 4, 5. So 4 plus 5, 9 estimates. Okay, and that's why degrees of freedom are 9. So here we can, when we are doing forecasting, we can take a look at our training data set, which would be all the data set, let's say up to June of 2006, and then we can apply different models on it, and then we can take a look at the fit of the model, and then once we know which model is the best, we can forecast using the model. All the models, in fact, in this we can use, and we can take a look at what is the forecast for 2 years ahead. So we're forecasting from 2006 to 2008. The forecast accuracy is going to be measured by the accuracy command, which is going to give you mean absolute scale error and mean absolute error, things like that. Okay, then we can say, well, the filter index is 2006 onwards. Okay, so here this is using different class of models. We are representing the root mean squared error. The models with the lowest AICC values tend to give slightly better results than other models, but AICC comparisons must have the same orders of differencing. The root mean squared error test set comparisons can involve any set of models. Okay, so use the best models available even if it does not pass all tests. So in this case, what we're doing is we're using PDQ 301012 as the model and then using it to forecast. And see, like, this is nice because this has tight prediction intervals for the sales. Okay, and this one, 301, what was it? 301012. So we're using 301012, this model right here. Okay, which gives us these tight forecasts.